Today is January 19th, 2023. It is 12:22 a.m. From Thomas's Calculus, Chapter 16.3. 16.3. Path independence, conservative fields, and potential functions. I will read this part. A gravitational field G is a vector field that represents the effect of gravity at a point in space due to the presence of a massive object. So, gravitational field is a vector field that represents the effect of gravity at a point in space due to the presence of a massive object such as Earth or Sun or Moon. The gravitational force on a body of mass m placed in a field is given by F equals mg. So G is gravitational field. If we multiply mass m to field, we have force. Similarly, an electric field E is a vector field in space that represents the effect of electric forces on a charged particle placed within it. So, an electric field is a vector field in space that represents the effect of electric forces on a charged particle placed within it. The force on a body of charge Q placed in the field is given by F equals QE. So, if we multiply E with charge Q, then we have force F. In gravitational and electric fields, the amount of work it takes to move a mass or charge from one point to another depends on the initial and the final position of the object, not on which path is taken between these points. In gravitational and electric fields, the amount of work it takes to move a mass or charge from one point to another. We are changing the position. The amount of work depends on the initial and the final position of the object. The amount of work, it means energy, not on which path is taken between these points, these positions. In this section, we study vector fields with this property. This property means the amount of work it takes to move a mass or charge from one point to another depends on the initial and the final position of the object, not on which path is taken between these positions. It means path independence. This path-independent property and the calculation of work integrals associate with them. In this section, we study vector fields such as gravitational field G or electric field E. These fields are called conservative fields. What the heck is potential function? What is potential function? What is conservative fields? Conservative fields in this case is a gravitational field G or electric field E. These are path independent. Path independence means the amount of work it takes to move a mass or charge from one point to another depends on the initial and the final position of the object, not on which path is taken between these positions. This is path independence. We study vector field with path independence property and the calculation of work integrals associated with them. What the heck is potential function? Conservative fields, path independence, all three things. Path independence, conservative fields, potential function. All three things, potential function, conservative fields, path independence, says one thing. Field, a vector field. in which the amount of work it takes to move a mass or a charge from one point to another depends on the initial and the final position of the object, not on which path is taken between these positions. We are going to learn a vector field that has path independence property. I said potential functions, conservative fields, path independence, all these three things says one thing. What is potential function? I do not film videos to teach my audience. I film videos to teach myself. Before filming this video, I did not quite know what the potential energy and the potential function means. Now I completely correctly understand what the potential functions are. I completely understand it now. Before filming this video, I watched these videos. These videos are very useful. In this video, I could correctly understand what the potential energy is. After watching this video, I could double check what the potential energy means. After watching this video, I could understand the relationship between the potential function and the vector field. We use gradient operation to generate a conservative vector field using its potential function. Then, using the conservative vector field, we can reconstruct its corresponding potential function. I would highly recommend these three videos. We have a function u, x, y, z. It is a scalar function and is called gravitational potential function. U is gravitational potential energy over mass over big object. So its unit should be Joule for gravitational potential energy. Its unit is Joule over mass of a big object. Its unit is kilogram. Now we have another potential function Vxyz, a scalar function, and is called electric potential function or just electric potential. It is electric potential energy over electric charge Q. So its unit is Joule per Coulomb. From gravitational potential, we create a vector field. It is usually denoted negative gradient u. Okay, this is gradient operator. It is defined delta u over delta s. Here we need negative. So its unit can be u, the potential function, Joule over kilogram. We divide with distance. Delta S is distance, so it should be m, meter. I would say kilogram meter unit. From electric potential V, we generate E. We take gradient with the electric potential function. V is electric potential function. This is delta V over delta S. So its unit should be Joule per Coulomb. This is distance. Delta S is distance. I will fix like this. Coulomb meter, because delta S is distance. For the sake of our discussion, we assume force F is constant both in the gravitational electrical fields. For the sake of our discussion, we assume the force F is constant both in gravitational and electrical fields. Actually, not constant, but we assume constant. Work in gravitational field W equals F dot S, because F is assumed to be constant. Then from this book, gravitational force F is mg. mg for F dot S. From this, m is mass, so its unit is kilogram. Then G, gravitational field, its unit is this. Then S, S is distance, so its unit is meter. From this, m cancels out, kilogram cancels out. We have Joule. Now work in electrical field W equals F dot S. Again, from this book, F equals QE. QE dot S. Unit of Q is Coulomb. Unit of E, electric field, is this. Copy, paste. S is distance, so m. m cancels out. Coulomb cancels out. We have Joule. In summary, U, a scalar function, is called gravitational potential function. Gravitational potential function is gravitational potential energy over mass of a big object. Its unit is Joule per kilogram. B is a scalar function and is called electric potential function. Electric potential energy over electric charge. Its unit is Joule per Coulomb. Using potential function, we generate conservative field G, conservative field E. G is gravitational field. Gravitational field is Joule per kilogram meter, or we can say energy density. In the same manner, using electric potential function, E is electric field. It is energy density. We used scalar scalar function or potential function to create or generate gravitational field or electric field.